Welcome to the Foundry by Forge College. I'm your host, and in today's explainer, we're taking those abstract key performance indicators we talked about previously and turning them into a living, breathing monitoring script for your Solana deployments. If you've been working your way through our Deploying on Solana track, well, you know we've got our theoretical blueprints totally sorted out. But let's be real for a second, there is literally nothing worse than your dApp suddenly going offline and you only find out because a mob of angry users starts tagging you on Twitter. You know, you're just flying completely blind. So today, we're stepping into the workshop to actually build the machine that gives you 20/20 vision over your infrastructure. Here is our quick engineering schematic for today. 1. The monitoring blueprint. 2. Gathering your tools. 3. Building the script. 4. The verification checkpoint. And 5. Preparing for alerting.
All right, Section 1, the monitoring blueprint. Let's map those KPIs to reality.
So, in our previous lesson, identifying KPIs for Solana applications, we spent a good amount of time mapping things out on a whiteboard, right? Stuff like latency, transaction throughput, and RPC error rates. But identifying them is really just step 1. There's a massive difference between theory and execution. Defining your KPIs was the what, basically a wish list of the health signals we care about. But actually fetching that live data straight from the blockchain, that's the how. Today, we're explicitly bridging the gap between those abstract concepts and the practical, hands-on construction we need to capture those critical signals in real time.
There is a huge engineering maxim we absolutely live by when designing these systems. Metric definitions alone are not useful without live data collection. Honestly, a blueprint is completely useless until you pick up your tools, get your hands a little dirty, and start building. I mean, you can have the most gorgeous dashboards sketched out in Figma, but until real bytes are actively flowing from a server into your database, it's just digital modern art. We need functional mechanics here, not just pretty ideas.
Okay, so let's dive into this mapping. I always like to think of a Solana RPC node as a heavily caffeinated, incredibly busy receptionist for the blockchain. If we want to understand our RPC latency, our P50 or P95 percentiles, we need to ask that receptionist a very specific question. We use getLatestBlockHash and simply time how long they take to answer. Why that specific method, you ask? Because it's the gold standard. It literally forces the node to check the current network state, so it can't just hand you a cached response. That gives us true latency. For our RPC error rate, we can monitor any RPC call and just count the HTTP errors. For block production, we ask for getBlock. And for recent performance, we use getRecentPerformance samples. We're essentially translating our human questions into exact programmatic requests.
Section 2. Gathering your tools. Let's set up the workshop. Since every good engineer meticulously organizes their workbench before making that first cut, let's get our digital workspace ready. 3 really simple steps here. First, verify you have Python 3.8 or higher installed. Second, create and activate a virtual environment. And look, let's just be honest with each other for a second. We have all experienced that classic developer rite of passage where you spend 20 minutes tearing your hair out over some bizarre import error, only to realize you forgot to actually activate your virtual environment. Save yourself the headache today. Finally, step 3, pip install requests and Prometheus client. We need request to talk to the blockchain and Prometheus client to package up everything we hear back.
Moving on to Section 3, building the script, assembling the actual machine.
All right, the workbench is fully prepped, so we're going to wire together a highly focused, maintainable Python script. Let's just name it Solana_monitor.py. I want you to think of this script as a diligent, remarkably lightweight health inspector. Every few seconds, this little inspector drops by your RPC node with a clipboard, checks the network's health, jots down the latency, tallies up any errors, and hands you a tidy status report. Now, the absolute emphasis here is on the word lightweight. We need this inspector doing their job without hogging your service CPU or bogging down the very infrastructure it's trying to monitor.
To share that report, our inspector is going to use the Prometheus exposition format. Now, I know, that sounds like a heavily intimidating sci-fi term. It literally sounds like something out of Star Trek. But actually, scratch that. It's really not complex at all. It's just a standardized, machine-readable text format for time series data. Think of it as a highly organized, universal language that structures our metrics so that future monitoring tools, stuff like Grafana, can easily scrape the data without needing custom parsers. It just makes our data universally understood.
Let's break down the anatomy of what we're writing. Up at the top, we establish our constants, like our RPC_URL and our poll interval. Right below that is the call_RP function, which handles sending our HTTP requests and tallying up our error counts. And finally, we have the record_metrics loop.
This brilliantly illustrates a fantastic engineering choice. We actually keep our metric storage in an ephemeral, circular in-memory buffer. Why does that matter? Because a super common rookie mistake is storing every single ping in a massive array. Do that, and your script is going to consume infinite RAM over time until your server just completely crashes. A circular buffer acts like a sliding window, keeping only the most recent data to compute percentiles locally. It makes the script incredibly fast, memory safe, and resilient.
Okay, listen closely to this next part because it trips up developers all the time. Ensure your schema is HTTP or HTTPS, not a WebSocket address. It is a super common stumbling block to just mindlessly paste a ws// address into your configuration. Since we are using the Python requests library for simple post requests, handing it a WebSocket address is going to cause instant traceback exceptions. Double-check that URL scheme right now, and you will save yourself hours of deeply frustrating debugging.
Section 4, the verification checkpoint. Let's flip the switch.
Our script is built, the code is saved. Now we power it on and validate that our engineering actually holds together in a real environment. But we have a strict acceptance criteria checklist before we can pop the champagne. First, the script must run for at least 3 polling intervals without throwing any uncaught exceptions. Why 3? Because 3 is the magic number that proves your script can handle natural network jitter, and it isn't just getting lucky on the very first poll. Second, it needs to actually print out non-empty numeric values for our P50 and P95 latencies. Third, our Prometheus endpoint absolutely must be up and actively returning those metrics.
If your script is running successfully, well, you've got a live diagnostic readout available to you right this very second. Just open up a browser and navigate to localhost 8000/metrics, or just run a quick curl command in your terminal. If the data is flowing properly, you are going to see lines of text showing your Solana RPC _P50 latency seconds and all the other KPIs we so meticulously programmed. Take a second to really enjoy this. It is an incredibly satisfying aha moment for any developer to see those actual numbers ticking by. Your machine is officially alive.
Finally, Section 5, preparing for alerting. What's next on the docket?
We've successfully built and tested our tool, which is awesome. But as we transition to the final stage of this explainer, we need to look ahead. What do we actually do with all this shiny new data? It raises a huge question. We have the live data flowing, but what do we do when things go wrong? Right now, our script is just a passive observer, standing in the corner taking notes. This perfectly teases our next step in the designing efficient monitoring strategies track, turning these passive observations into proactive alarms that will literally wake you up if a critical node goes down.
Before we get there, though, I'm assigning you a bit of engineering homework. Run your new script for an hour. Export a CSV or save the JSON output. You need to gather a realistic sample dataset to establish your baseline noise characteristics. Every single node environment has its own baseline latency. Think about it. If your node naturally hovers around 200 milliseconds of latency during normal operation, and you blindly set an alarm for 150 milliseconds, well, that alarm is going to fire constantly, and you will never, ever sleep again. You need to know your normal so you can spot your abnormal. Establishing these baselines is absolutely critical for preventing alert fatigue.
I want to leave you with this provocative thought. Does your monitoring script just watch, or is it ready to defend your deployment? Passive monitoring is a great first step, for sure, but active defense is the ultimate goal. Learning with Forge College programs helps you answer these exact engineering questions, moving you from a builder to a true defender of your infrastructure. To take that next step and dive deeper into more Web3 insights, be sure to visit forge.college. Thank you so much for joining me on this explainer, and hey, happy building.